right, so I made the mistake of telling you that I was going to turn something in on Friday, and so that means that I'm here. I'm right now in the physics clubhouse at 10:25 tonight, since I didn't get to this yet till now. So anyway, there's still work to be done, but I got to get something turned in, so that's this. So this is the Fabry Perot lab, and I think actually this was lab number 4, so I'm going to change that right there. Okay, in this lab we calculate the free spectral range. Our group, we did a hot red laser and a cold laser using the Fabry Perot instrument. The wavelength of a helium neon laser is 632.8 nanometers. However, what we're measuring is the amount of variation in wavelengths. So, and actually, I could call it, and that is essentially the free spectral range, is how much that varies. So this diagram right here, I tried to draw. So we've got a, this is just it was an arbitrary drawing, but 328 nanometers. What happens though is that you get a little bit that's just a little bit longer or just a little bit shorter, and that interferes with that. However, in the Fabry Perot device, what we're doing is we're putting, I believe it's silver, so we're using silver to that we're transmitting the light through, and then it bounces. Then some is going to bounce right back off, angle in equals angle out, as I learned in my oral, or I was reminded of. And then some will just immediately do that, but some is going to go through, and then some is going to then directly go right through again. But some is going to bounce back and then bounce. So, and what's the difference between these two? Well, that is, it is, the difference there is, the difference in phase between these two, between a light that's done that is, well, is two d, the distance between there. So how do we use this device to capture the spectral range? Well, what we're doing is we can use this property, the fact that light bounces, and we can basically slow down the transmission of one of these. So if we could just slow this one down using this device, we could get that to line up here and create a big peak. And that is what we're doing here in this experiment. So we can easily derive, which I don't have the derivation, that the free spectral range wavelength is the wavelength squared, and that is the 632.8 nanometers divided by 4d, and that is that. And the d that we find, that is, what we're doing to find that d is that we're adjusting the spectrometer until we get to a point where the big peak, the first peak of 1, can match up to what's that distance from where until that first peak lines up with the of the next wavelength of the next wave, and then that's where we get that. Insert my picture here. Yes, I've got to get a picture loaded in here too, and then data. Our data shows. So I've got data, but I just haven't fully put it in yet. Then our air, got to propagate it, and then our conclusions. As our data analysis shows, which has not been done yet, the spectral range of a hot laser is blank, and of a cold laser is blank. So that is my first submission here of Fabry Perot.